What I'd like to talk about now is I'd like to talk about basic shapes of trig functions. In algebra, I tell my algebra students that as soon as I say f of x is equal to x squared, they should have a particular picture jump to mind, in other words, a parabola. For trig, I will tell you that when I say sine of theta is equal to y over r, you should have a picture jump to mind as far as its graph. First of all, I want to make a distinction between how we normally draw triangles as far as x, y, and r values and the set of axes that we use for that. And I want to say that we use a different set of axes when we actually draw the functions sine theta equal to y over r. What I mean, it still looks like we draw a vertical and a horizontal axis, but we don't have an x-axis and a y-axis. Instead, the horizontal axis are values of theta, and then the vertical axis is the y value for this, I'm sorry, not the y value, but the output for this function. The output for the function is the value y over r. So depending on which trig function we're graphing, the horizontal measure will always be theta, angle measures, but the vertical axis is going to be the value of the function that we're using, in this case y over r. The first thing I'm going to do is I'm going to talk about before we restricted the actual values you could get out for sine, and we found out the restriction was in between positive 1 and negative 1. So we can't go above positive 1 and we can't go below negative 1. The second thing I'm going to do is I'm going to talk about, for sine, what we call quarter points. Quarter points basically is we're breaking up our trig function into 4 pieces, and if we look at these 4 pieces, then the sine function cycles through 1 period during these quarter points. These quarter points, without explanation, are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, this should make sense because you can think about on the axes that we normally draw triangles for sine, then you start at the angle measure 0 and you go all the way to the angle measure 2 pi. Pi over 2 we know is 90 degrees, and so what I'm doing is I'm breaking up the interval from 0 to 2 over pi, to 2 pi into equal pieces by using 90 degree measures. So I have 0, pi over 2, which is 90, pi, which is 180, 3 pi over 2, which is 270, and then 2 pi, which is 360. You can make a t-chart, and if you make a t-chart using these values of theta, and you plug them into sine, and you figure out the corresponding value of y over r, this is what you will find out. You will find out that when you plug in the angle measure of 0, you get that the sine value is also 0. If you plug in pi over 2, you find out that the value you get out for sine is positive 1. If you plug in pi, you find the value is 0 again. If you plug in 3 pi over 2, you figure out the value is negative 1. And if you plug in 2 pi, you find out the value is 0. Plugging in increments in between these angles will complete the chart, and it will give you other points that will determine that the shape of your function should look something like this. Now, this is the graph of sine over 1 period, but sine is cyclic. In other words, I can plug in any angle measure for sine and I can get a fine value out. So actually this graph continues on in this pattern to the right of 2 pi and to the left of 0. But it continues this exact same pattern. In other words, if I was to make a copy of this graph and extend it on to the right and extend it on to the left, then you would see a wave function. Alright? This particular graph is the graph that you need to know when I say what does the shape of sine look like. The distinguishing characteristics is that at my quarter point 0, I end up with the value being 0. And then from there, I actually go up to positive 1. Notice that I rotate in between 0, 1, and -1. And the way I know when I rotate is I rotate on quarter points. In other words, my first quarter point is 0. I need to know my value is 0. My second quarter point is pi over 2. I need to know I go up to +1. But then after that, I would know basically for free what my other values are. In other words, I've gone up to 1, so I now know it's time to bounce back down to 0 at the next quarter point, bounce back to -1 at the next quarter point, and then come back up to 0 at the last quarter point. Memorize this graph, understand it, but memorize it as far as the shape. Number 2, for f of theta equaling cosine of theta being the value x over r. The horizontal axis is once again theta, and the vertical axis is the value x over r. We found out the restriction on the range of cosine is anything in between 1 and -1. Once again, we're going to have the same quarter points as we did for sine. So we're going to have 0, pi over 2, pi, 3 pi over 2, and 2 pi. The difference is if you were to create a t-chart and you were to plug in values for theta, you would find out in this case if you plugged in 0 to cosine of theta, you would end up with a value of 1. And so your first point is actually at +1. If you plug in pi over 2 into cosine, you find out the value is 0. If you plug in pi, you'd find out the value is -1. If you plug in 3 pi over 2, you find out the value is 0. If you plug in 2 pi, you find out the value is 1 again. Okay, you're seeing that you're bouncing in between 1, 0, and -1. Okay, the basic shape, if you were to fill in the points in between, would end up looking something like this. Once again, we actually have a continuation, so this graph would continue the pattern both forward and backward in this cyclic pattern. You need to know that this is the basic graph for cosine. What's the difference between cosine and sine? The huge difference is while sine starts at 0, 0, cosine starts at 0 and 1. You still have the cyclic pattern of at the quarter points, you're rotating between 1, 0, and -1s. For tangent, tangent's slightly different. For tangent, we found out there is a restriction on the values that you could actually plug in for theta. We said that we could not actually have odd values or odd multiples of pi over 2. Since I'm graphing only one period of tangent, what I'm going to do is I'm going to say, okay, what's the first value to the right of the y-x axis that I can't have? That first value would be pi over 2. I'm going to indicate that I cannot have my angles equaling that value by drawing a dotted line. This is actually a vertical asymptote at pi over 2. Now I'm going to go to the other side and say, well, I also couldn't have negative pi over 2 as a value. That's also an odd multiple of pi over 2, so I'll put an asymptote on that side as well. Okay, now my vertical axis is actually not an asymptote. I don't have any problem with theta equaling to 0. That's not a problem at all. So in this picture, the only two asymptotes I have is negative pi over 2 and pi over 2. Now, that being the case, this is going to change the quarter points that I would normally have in sine and cosine. If my first quarter point is negative pi over 2 and my last quarter point is pi over 2, then the quarter points in between are going to be slightly different. All right, think about my middle quarter point. I know would end up being 0. What's half the distance between 0 and pi over 2? Half that distance is pi over 4. The same thing the other direction, half the distance would be negative pi over 4. From here, what I'm going to do is I'm going to label special points that I have in the graph of my tangent function. Okay, it ends up that my tangent function goes through the point 0, 0. To the right, I have a special point at 1 and that first, second, third, fourth quarter point. The fourth quarter point would be here. I also have a special point at -1 and the second quarter point. It turns out that the graph of tangent looks similar to a cubic function. In other words, on the right, it kind of bows out and then it gets pulled toward the asymptote. It will never touch that asymptote, but it gets pulled towards it and goes to infinity on the right, and then down and to the left, being pulled toward the asymptote, -π/2. Once again, I get this graph by making a t-chart, plotting tangent at -π/4, at 0 at π/4, and these are the values that I get. The 1 and the -1 in this case are what I would call special points, and you need to know where those are located. The big thing for tangent is the right-hand side goes up, the left-hand side goes down. When I finish these graphs, I will talk about something called period. The period for tangent is different from the period for sine and cosine. Let's now talk about the cotangent function. With not too much explanation, I'm going to say that we have a vertical asymptote along the xy axis, so a vertical asymptote at 0. It turns out we also have a vertical asymptote at pi. All right. For cotangent, we had found out that we cannot have any kind of integer multiple of pi. Quarter points between 0 and pi. First one is obviously 0. The middle one would be π/2. That being the case, this one would be π/4, and this one would be 3π/4. Special points for cotangent. On the middle quarter point, you're actually on 0. Instead of going up on the right like tangent, you go down on the right. So here you'd have -1, and then at the 3/4 quarter point, you'd be down. And then on the other side, you'd have +1, and at the π/4 quarter point, you'd go up. And your graph looks something like this. So a big difference between the graphs of tangent and cotangent. They have similar shapes, but they're opposite in direction, and they also have different quarter points.